This is our glider project. I'm Madison.
And I'm Dridi.
So for this project, we were tasked with building a balsa wood glider and applying the principles of aerodynamics. The most important requirement was that the glider would fly at least 20 feet when hand thrown on level ground and stay intact. Some other notable requirements were that it had to fit in a box that was 16 by 16, and we were only allowed to laser cut 2 sets of the components, so we had to design carefully. So our main strategy for the design process was to get the glider to fly 20 plus feet while meeting the other requirements. So we would do this by maximizing lift to drag ratio, and to do that, we had to pay attention to certain key factors.
So for our first design alternative, we were deciding between compound wings and double tapered wings. So for the compound wing, while it is easier to make dihedral angles, its larger surface area means a lower aspect ratio. And for the double tapered wing, this would make our manufacturing process much shorter. But less area on the wing does mean less lift. However, this does mean a higher aspect ratio, so we went with the double tapered wing.
Another thing we were deciding between was between the conventional tail and the T-tail. A lot of real-world gliders have T-tails, like the one in the picture. However, you do need a larger vertical stabilizer, which makes the plane heavier, and there's also the possibility of deep stall, so we went for the conventional tail instead, which has a lot more information on it readily available.
For our third design alternative, we were deciding aspect ratio and mainly how it had to do with the wingspan. So with the 20 aspect ratio, the wings would be really thin, even though real world gliders have an aspect ratio of at least 30. And for the 12 aspect ratio, this kind of went based off of the model gliders, which typically have it from 6 to 12, and a larger area does mean easier manufacturing. So we compromised at 16. This was our chosen design.
So for the wings, we ended up going with the linear taper. They're simple to manufacture, and then we chose the taper ratio of 0.45, which minimizes drag. And then, as we mentioned, we chose an aspect ratio of 16, which is a good balance. And then we decided to maximize wingspan so that we could maximize the aspect ratio. So we wanted to go diagonal with the box, so we made our wingspan 20 inches, and then our wing area was 25 square inches. Our fuselage, when we were deciding this, we had to mostly decide on the length. So the longer fuselage generally, the more stable the plane becomes, and you can also make the tail fin smaller. However, it does make the plane heavier. So we experimented with different lengths. Anywhere between 0.5 and 0.7 of the wingspan is pretty optimal. So we first went with the 0.7 of 14 inches, and then we decided to decrease it to 11 inches because it performed best.
And for the stabilizers, these areas were mainly based off of research. So for the horizontal stabilizer, this was 20% of the wing area, and for the vertical stabilizers was 10% of the wing area. And again, we used the conventional tail configuration. So our first prototype was with cardboard. This was 1-to-1, and the max flight distance was 22 feet. And the adjustments we mainly made were just figuring out where to place the wings on the fuselage, and then also the fuselage length. This was cut unevenly and lacked durability, so we moved on to the balsa wood.
So here's some pictures of our balsa wood first design. It was a little bit imbalanced, so we had to add clay to one of the wings. And then we did a lot of tests on our first design. We first added Play-Doh to the nose, but then we chose clay because it was more dense. And then we used clay to correct the imbalance between the wings as well. We played around with where the center of gravity would be for it to fly best, and we ended up getting a max average distance of 27 feet.
So some modifications we plan on making were to shorten the fuselage from 14 inches to 11 inches because this meant less clay needed to shift the center of gravity forward. And then we also cut the stabilizer symmetrically because originally they were off because we incorrectly exported the DXF files when laser cutting.
So for our final design, we kept the wing design the same, but we did shorten the fuselage to 11 inches. And then our stabilizers are also the same as originally. We just made sure that they would be cut out as they were drawn. And then our final design, here's some pictures. The left is the SolidWorks model, and then on the right, it shows our railroad model fitting into the 16 by 16 box as required. The overall weight was 9.9 grams for the balsa and 11.3 grams for the clay.
For our center of mass calculations, we calculated the center of mass using SolidWorks for the balsa wood glider. The part at the front you can see is the clay. So we actually measure the masses of the glider and the clay in the AMS. So then we use this to do our center of mass calculation. We multiplied the masses by the distance from the nose tip, which gave us 2.673 inches from the nose tip. We also calculated the quarter chord point, which was 2.8125 inches. The static margin calculation, we used the quarter chord point and subtracted the center mass from that, which gave us 0.1395 for the static margin. And then we also calculated the mean aerodynamic chord and then represented the static margin as a percentage using the mean aerodynamic chord.
So here's the video of the competition. We ended up flying 36 feet, which cleared the 20 feet requirement. However, we did have a slight imbalance where the glider was veering off to the right. So based on the video, the angle of attack was about 8 degrees. So we were able to calculate the lift and drag coefficients. Based on that, our lift coefficient was about 0.88 and our drag coefficient was about 0.034. So that gave us a lift to drag ratio of 25.7. So final thoughts, overall, we did very well. We cleared the 20-foot requirement by quite a bit, and I would say a lot of the decisions we made with our design were well within the optimal range, like the angle of attack, the static margin, and the lift to drag ratio. However, we could have improved if we had more time. We would have liked to go through a more mathematical process for how we sized the stabilizers because we mostly just went by the area and then everything else was kind of arbitrary. And then based on gliders that did well in competition, we would have liked to improve the dihedral angle, add winglets, and try and balance the wings better. Here's our sources. Thank you.
Thank you.